We begin our analysis with a single, slow-moving thermal neutron steadily approaching a massive, highly unstable uranium-235 nucleus. The collision triggers a sudden, violent collapse of the nucleus, releasing roughly 200 million electron volts of energy. This exact process is nuclear fission, a heavy nucleus dividing into roughly two equal parts, occurring either spontaneously or by targeted induction. The physics restrict this phenomenon. Only heavy elements with a mass number greater than 230 are vulnerable to this specific type of low activation energy split. While certain elements decay naturally, bombarding the nucleus with neutrons or charged particles allows us to force this reaction on demand. To understand how this microscopic division powers cities or levels them, we have to analyze the mechanical forces holding the atom together and calculate the strict mathematical ledger of its destruction. Splitting an atom is about exploiting a precarious instability inherent in the universe's heaviest elements. Let's scale down to the microscopic level to examine the internal forces of a heavy nucleus before it is struck. This diagram illustrates the liquid droplet model. It conceptualizes the nucleus as a sphere of liquid maintained by a delicate equilibrium. The strong nuclear force acts like surface tension. It pulls inward, attempting to hold the nucleus in a perfect sphere. Opposing that inward pull is Coulomb repulsion. The positively charged protons constantly push outward, trying to tear the nucleus apart. When the nucleus absorbs an additional neutron, that perfect sphere distorts into an elongated shape, oscillating violently as the two internal forces battle. If this distorting force overcomes the surface tension, the droplet elongates past a strict threshold and physically splits. We measure this vulnerability using the fissionability parameter, calculated as the atomic number squared divided by the mass number. An increase in the atomic number exponentially increases the proton repulsion, while the mass number provides the baseline for the volume. A high fissionability parameter indicates the nucleus is primed for self-destruction, requiring only a tiny nudge to shatter its equilibrium. Atoms rarely split perfectly in half. The division produces a probabilistic mixture of chemical fragments. This equation shows spontaneous fission. Highly unstable elements, like californium-252, undergo this split without any external trigger, breaking naturally into barium-142 and molybdenum-106. Induced fission operates under different rules. When we bombard uranium-235 with thermal neutrons, we see a wide range of results. This chart reveals that the uranium-235 reaction does not have a single outcome. It branches into multiple possible sets of chemical products, yielding pairs like xenon and strontium, krypton, or rubidium. In low-energy thermal reactions, the nucleus heavily favors asymmetric fission, meaning it splits into unequal masses. The ratio of the light fragment to the heavy fragment typically stays around 2 to 3. If the energy of the bombarding particle increases, the symmetric mode dominates, forcing the atom to split evenly into roughly identical masses. Regardless of the exact pathway, the process yields exactly two primary fission products, resulting in a 200% total yield per event. The specific identity of the resulting fragments is a subatomic probability governed strictly by the energy of the initial impact. To understand exactly where the 200 million electron volts of energy comes from during this split, we have to track the mass.
Binding energy per nucleon peaks around 8.4 MeV for nuclei with atomic numbers between 80 and 135. The newly formed fission fragments land squarely in this more stable range. They possess roughly 0.9 MeV higher binding energy per nucleon than the original uranium. Transitioning to this higher stability requires the physical destruction of matter, a phenomenon known as the mass defect. Let's set up a mathematical ledger. When uranium-235 absorbs a neutron, it briefly becomes an unstable uranium-236 nucleus with a resting mass of exactly 236.135 atomic mass units. We can tally the mass of a specific resulting product set. Molybdenum-95, lanthanum-139, and two spare neutrons combine for a total mass of 235.918 atomic mass units. Subtracting the final product mass from our starting mass leaves a discrepancy of 0.215 units. That missing matter is converted entirely into energy. Multiplying the 0.215 defect by 931.5 calculates out to our total yield of roughly 200 MeV. This energy is distributed across the resulting particles: 5 MeV to neutron kinetic energy, 5 to beta decay, 12 to gamma rays, 11 to neutrinos, and the vast majority drives the immense kinetic energy of the heavy fragments themselves. The immense power of fission is the physical manifestation of vanished mass, perfectly balancing the universe's energy ledger. While the heavy fragments contain the physical force, the ability to scale this reaction lies in the 2 to 3 free neutrons ejected during the split. This diagram outlines the vectors. These free, high-speed neutrons fly outward to strike neighboring uranium atoms, inducing further fission. The condition for a chain reaction is strict. At least one neutron from the first generation must successfully initiate a second generation. As this slide from our source data details, the probability of a sustained reaction requires an equilibrium between 4 opposing factors. The first 2 factors are the raw rate of neutron release versus the rate at which uranium simply absorbs a neutron without splitting at all. The last 2 factors are neutrons being captured by non-fissile impurities in the surrounding material, or neutrons simply escaping the system entirely. These factors determine the effective neutron multiplication factor, represented by the variable K. This measures the average number of neutrons from one event that successfully cause another. If K is less than 1, the reaction dies out. If K equals 1, it maintains a steady state. If K is greater than 1, the reaction grows exponentially. Mastering nuclear physics requires manipulating these 4 physical variables to control the K factor. This facility is a controlled K equals 1 environment. Engineers use moderators like graphite to slow down neutrons and maintain a steady state of continuous output. Push K over 1, and the release of this massive amount of energy per unit time results in an uncontrolled explosion. A microscopic yield of 200 MeV equates to roughly 3.2 times 10 to the negative 11 watt-seconds. Scaled up, a single gram of uranium-235 contains enough fissile atoms to produce 2.3 times 10 to the 4th kilowatt-hours of energy. Achieving that same 1 megawatt-day of energy requires burning roughly 2,500 metric tons of coal. The threshold of a liquid droplet, the conversion of a tiny mass defect, and the strict mathematics of the K factor combine to make nuclear fission the most dense and powerful manipulation of matter humanity has ever achieved.